just coming here made me realize how much better an in-person conference still is. It doesn't even compare. So it's been really great being here again.
Thank you so much for joining. My name is Milad. I do robotics and software in Johnson Johnson MedTech. So this year is my first year being at CppCon, and also my first year, obviously, giving a talk. So when I submitted the presentation, I think it was just myself with the abstract, but because Alex Rue, my friend and colleague, he actually helped out from 0 to 100% of the presentation, feedback on everything. And I basically asked him to co-present with me, and he kindly accepted. Alex.
Yeah, hi. So I'm Alex Drew. I work as a software engineer for Johnson Johnson in MedTech. Work with Milad closely doing surgical robotics. Got a couple more of our group in the crowd, and hope you all enjoy the talk.
Yeah. All right, so going back to the title of the talk, it's a mouthful. So there's a lot of component that goes to building a robotically assisted surgical platform heavily using C++. Today, we will basically just touch upon very high-level concepts. For those of you who have been around in medical devices for a long time, I think it's gonna, at least the introductory part would be like a refresher. But for the rest of you with no medical device background, I hope it's gonna be beneficial. So just some legal stuff for the external engagement disclaimer. Basically, all the content is myself and Alex's opinion, and they don't represent the stance or view or official position of any company within J&J family of companies. So big picture, what do we want you guys to take away? What's the big picture in the talk? First, we're gonna talk about why we care about safety and security. Probably in this conference, you guys have heard a lot about this in the past few years, but I'm gonna just repeat just tiny bit. And then we're going to talk about the medical device failure analysis and what causes medical device recall and failure based on some database from FDA, Food and Drug Administration. And then we're going to talk about briefly, maybe 5 to 7 minutes, just talk about what we have, what are the guidelines, what are the regulatory documents, standards, and reports, and to ship a software as a medical device for a product. So, and then we're going to talk about safety in CPP specifically, what we can do beyond the guideline and standards to have a safer usage of C++, especially in medical devices. And then we're going to talk about some coding practices and code examples in CPP within safety critical path for any safety critical product, especially medical devices. And then at the end, final words and Q&A. So we have probably about 50 minutes worth of content, I would say. And then at the end, we can take any questions and feedback you guys have. So let's talk about safety and security in CPP. I think you guys have seen a lot of these reports in the past 2 years from NSA regarding protecting against software memory safety issues and using memory safe languages, from CISA, for a few revisions, and then from White House to revision on basically the bottom line or the common denominator for all these reports are stay away from memory unsafe languages like C and C++ and rewrite your software or write new software using memory safe languages. That's the common denominator. Although I think all of them, they acknowledge you could do a lot of software hardening on the C and C++ language to essentially, but to make the usage safer, but because we can't kind of guarantee that safety, they say stay away from those languages. So most of these reports, they actually refer to common weakness enumeration or common vulnerability and exposures databases from MITRE. And I think you guys have seen this from many other presentations. Basically, for example, for 2023, they have a list of top 25 common vulnerabilities. As you can see, many of them are actually language agnostic. They could happen in any memory safe languages as well. But the ones that I have listed here, that I've highlighted it, they can happen in C or C++ specifically. So for all of us who have written C++, we probably have run into many of these issues like out of bound write or race conditions, use after free. And most of them are basically based on the Microsoft and Google Chrome reports on memory safety issues. For example, the use after free based on the Google Chrome bug report on the security perspective, 30% almost was purely based on use after free. So ever since 2 years ago, maybe from many years ago, but especially 2 years ago, there has been a lot of activities, a lot of recent talks from ISO CPP notable committee members, the C++ community on what we can do from a language perspective to make C++ safer. Some of them, they talk about software hardening. Some, they take a philosophical approach. Can we even save C++ and things like that? But mostly they tackle it from a language perspective, what to do to make CPP safer. But in our talk, the idea is, forget about this. We talk about the software hardening on the medical device example, what actually we can do to guarantee some sort of safety by using C++. So let's talk about medical device failure analysis and what actually causes medical device failure and recalls based on some data. So in 2013, this paper, they looked at FDA, Food and Drug Administration MADE database from 2006, 2011. They basically look at all the medical device failure and recalls. Some of them, they could cause injury. Some of them, they could cause a lot of failures and maybe death at some cases. And without considering security, the conclusion was 64% of software the medical device failure was actually due to software. Another database from Stericycle Expert Solution, they have a recall index database for many different industries, such as defense, avionic, automotive, and also medical devices. This one is specific to medical devices. They looked at the data from Q2 2016 to Q2 2018, and again, their conclusion was software for the 9th quarter in a row was actually the top cause for medical device failure and recall. We have tons, millions of medical device failure and recall for each quarter, basically. So that's tons. And given the ever-increasing complexity in software, in medical device market, there is a lot of demand for more complex software. And you have more complex software, you're going to have a lot more issues because it's very hard to manage. And then we have a new threat, cybersecurity. So given the cybersecurity and software being super complex, software is and will be the core of the many issue, maybe the top cause even. When we talk about software, we don't necessarily say the UI part of things. We talk about the software design, the implementation, the usage of languages and things like that. So now let's shift gear and talk about some of the standards and documents we have for medical devices that at least gives you some sort of guarantee to have a safe medical device. So I believe it was probably 80s, the Therac 25, probably you guys have heard of it. They call it the nastiest bug in the software history. So Therac 25 was a radiotherapy machine that because of there was a lot of software issue with it, a lot of different components, but at the core, there was a race condition in the 80s that caused the system to fail and overdose patients with radiotherapy, and it killed dozens and injured so many people. So ever since, government, a lot of regulatory agencies, the medical device community, they have got together to actually address the issue with software in medical devices. And we have tons and tons of different standards, reports, and documents in medical devices to ensure software is safe. So going from quality management system standards, to risk management, to usability, health software, security, application of agile to medical devices, AI and machine learning guidances, and specifically on the cybersecurity. They put out a report in 2023, pretty comprehensive on cybersecurity for medical devices. And 2024, they actually had a revision. I didn't bring it here, but it's a draft still. But given the complexity, given the increasing complexity with cybersecurity and all the attacks, they keep updating these standards because they have to keep up with the increase in the attacks. So one of the most important documents we have in medical devices that I'm going to talk about maybe for 2-3 minutes is actually IEC 62304. This one is similar to functional safety for automotive. If you guys have worked in automotive, they have functional safety standard. It's very similar to that standard. So IEC 62304, functional safety. So basically, this document doesn't tell you how to do things. It tells you kind of what to do from development and design all the way to manufacturing, distribution, and post-market release. And then it starts by talking about, I'm not sure if it's too obvious here, but I'm going to explain it. The vision is not so good. So basically, first, it classifies different medical devices. So you go from Class A, Class B, Class C. Class A, software failure does not cause any injury whatsoever. Class B, it could cause some injury, software failure, but the injury is going to be minor. But Class C, which is the kind of highest risk class, software failure could cause serious injuries, and in some cases death. For example, the system that we work on, the robotically assisted surgical platform, that's a class C because you have robots, you have instrument inside the body, and software failure could actually cause severe injuries. And then they basically talk about software risk management, software development and planning, and all the way to software release, software configuration management, software problem resolution, and also software maintenance. So specifically on the software development planning, their largest section is on development planning, architectural design, all the way to software detail design, to unit testing, integration testing, and all the way to software release in a cycle. So like I mentioned, they don't say how to do certain things. They basically tell you what to do. So they bring up a lot of examples. For example, you can use like the V model for software development, which looks like the waterfall model, but it's been very successful from the 90s and 2000 in many safety critical environments. But because it resembles the waterfall model and the requirements could be set in stone without any change, kind of no continuous deployment, continuous incremental changes, Amy came up with this technical report in 2012 to apply the practice of Agile and Scrum to V model. The combination of these two is actually the ones that many of the medical device companies, they practice to stick to Agile format. Another important document in medical devices is the principle of software validation and verification to medical devices. So here the emphasis is testing. So we can do anything to avoid failures, to prevent failures. But at the end of the day, some failure could happen, right? The problem is we have to ensure, basically we have to fail safely, or a fail-safe design. So here, the idea is you have to have 100% coverage. That means if you add like a one line of code, you have to cover it. How? You could use unit testing. You could use integration testing to actually cover that piece of code. You can do end-to-end testing. You can do fuzzing. You could do penetration testing. You could do a bunch of different testing to ensure your software is 100% covered. So the reason is we want to kind of catch errors, catch bugs, catch problems way early in the process. If you catch problem in the design phase or unit testing phase, that's going to be exponentially less expensive if you catch it in the post-market release. Very important document here, TIR 80002. They talk about the application of software, the application of medical device risk management to medical device software. So one example is, so you basically have the software failure item, and then you're going to have some sort of risk control measure, and then you have some sort of verification type that they give you tons of example. Once the software failure happens, for example, they say if you have a memory leak in the safety critical path, what is the risk control measure you can do? You can avoid dynamic memory allocation at the critical path. And how can you verify this? They actually give you the inspection way, using unit testing, implementation testing, or using static or dynamic analysis tooling. They have tons of example race condition. You can find this in this report. They have like more than 200 examples on if a software failure happens, how could you do the risk control measure, and how can you actually verify and document and submit to FDA. The last piece about 62304 is the concept of SOUP, SBomb, and CBomb. So SOUP, as you may know, is a software of unknown provenance. So anything you do not develop in-house is considered as SOUP. Your third-party libraries, your operating system, even your compiler, that's part of your SOUP, software of unknown provenance. So SOUP has to be absolutely tested, verified, documented, and validated. Even your compiler, the output of the compiler has to be validated and submitted as a document to FDA. So the other concept is SBomb. You've heard this probably in many other talks, software bill of material, and CBomb, cybersecurity bill of material. Those two are pretty much interchangeable. So we can use them interchangeably. SBomb is basically the software bill of material and includes a giant, you have to generate a giant document and submit it to FDA that has all the software items you use, including their version, their author, their supply chain transparency, anything that has basically everything about that software has to be documented properly. Maybe the government, they have their own version of SBomb and they can match these two to find out if you have essentially ignored any sort of vulnerability within a software. I believe even right now, at least from 2 years ago, if your company even doesn't do safety critical work, but you contract with government, most likely they'll require you to submit an SBomb for the third-party library used due to cybersecurity vulnerabilities. Switch to this one. Can you turn this off or, okay. All right, can you guys hear me well? Perfect. Yeah, so let's go to, okay, so we talked about all this standards, we talked about all the regulatory stuff, but is it really sufficient when we have a software as medical devices? Is it sufficient that we essentially just stick with the guidelines and ship a product? We have millions of software recall, the medical device recalls, medical device failures. So in my opinion, the answer is no, because the language of these guidelines and standards are actually very, very high level. They are not super prescriptive. So even at the beginning of the document, they say anytime we say you should, that means it's a recommendation. They specify that literally and say should means recommendation. Doesn't mean you have to do it. So they might tell you, yeah, static analysis tool, it's fine, you can use it, but they don't require it to use. They don't tell you how to do, which is both bad and good, but it's very, very high level. Perhaps actually the guideline in medical devices are maybe less restrictive than automotive or maybe avionic or defense or industrial technologies. So we have to do a lot more than just sticking with the guidelines. There was actually a pretty interesting survey by the Bar Group in 2018. They surveyed many different companies in safety critical system. Perhaps 66% of those companies were in medical, defense, automotive, and industrial technologies. And they were asking probably near 2,000 of their employees of all these companies some questions like, do you use regression testing? Do you even follow some sort of standard? Do you use static analysis tool? And mainly on the safety critical path and embedded system. And the results for me, although may not be completely correct for every single company, but the result was a little bit alarming to me. Like, for example, the 41% don't perform regression testing. 1 in 6 designers in those companies, they were completely ignoring security by design. 33% don't perform static analysis tooling, like things that are right now considered as basic, like code review. 43% don't even do code reviews. Those things are extremely alarming for safety critical and embedded systems whether it's defense industry or medical, automotive, or industrial technologies. So what do we want to achieve from a software as medical device perspective? We want to achieve functional correctness, we want to achieve functional safety, and we want to achieve security. What's the definition from a medical device perspective? What is the definition of functional correctness? In my opinion, you have a product, you have some specification, you have input and output, deterministic way. If you can validate and verify your specification of your system, then your system is functionally correct. Functional safety is, I do not mean any unintended behavior, 0 unintended behavior for the medical device. Anything, the failure could happen, but the system has to fail safely. If I give an input to the system, I expect output, but I cannot prevent every single failure, right? And system could fail, but I have a fail-safe design in place. So if every single layer fails, probably I have some hardware level that prevents me from injuring the patient, essentially, at the end of the day. And security, protection of system, network, and data from damages, theft, unauthorized access, and attack. So now let's talk about our use case that we use CPP and in medical devices. So for our use case, we obviously can't talk about many things because the product is not released yet. It's not even been submitted to FDA, maybe anytime soon. So we have a robotically assisted surgical platform. This system is a Class C product, so that means software failure within the system could cause severe injury or death to the patient, right? So this system is extremely complex. I have worked in manufacturing, I have worked in medical devices. Building a robotically assisted surgical system is extremely complex and hard, actually. That's why we have only probably one single dominant player in the market in the past 30, 40 years. So in this system, we have a robotically assisted surgical platform with perhaps multiple kinematic chain of control and robotic system with more than 75 degrees of freedom. You have AI vision components. You have complex clinical workflows, complex clinical modes. You have very complex UI and UX components. You have middleware. You have to target many, many different platforms. You have many different compiler for your system and many, many more components that almost all of them are written in C++. So you have millions of line of code in C++, right? So what can we do about this? So maybe this question that I'm asking in this slide this is CppCon, all of you write CPP code, might be pretty simple, why people use C++, but I just want to allude to some part of it. and I think it's very important and sometimes could be overlooked. So we talk about memory-safe languages, right? So we say NSA, White House, they all urge you to write with memory-safe languages, for example, like Rust to replace CPP or write new code with Rust. So CPP, very large and active community, performance from a high-level language, I can claim pretty much unmatched. We have a lot of standard framework libraries, but one important thing that is often ignored is the interoperability, portability, and compatibility of C++. So right now, let's say if you use some sort of real-time operating system, you use some sort of middleware. So pretty much the dominant vendors in the market, they are safety verifiable or they are safety verified. They do not support memory-safe languages. The only languages they support perhaps is just C++. So even if you want to write things in Rust, either you have to completely switch from those vendors or you use something else, then you can't use like memory-safe languages those occasions. So you have to use C++. So now that we use C++, what can we do from a software perspective to make the usage of C++ safer? So there are many components. We have categorized this in kind of 5 categories. First, I would say we can start from culture. So in medical devices, every single developers, when they write code, they have safety in mind. So although culture may not be super duper scalable, but when they write a single line of code, when they address a bug, they make sure they write a unit test for it, for example. If they have one line of code, maybe it's an exaggeration, but they think about it, am I gonna hurt a patient? Am I going to, could this bug could cause severe injury to patient? So it's very important to have a strong culture on safety. The second one is architecture. So architecture facilitates many things, a good architecture. We have to make sure the architecture is modular enough, has a great separation of concern, has a lot less coupling, and all the good stuff that we know about architecture, because that enables us, if one day I wanted to rewrite a component of my software in memory-safe languages, I'm going to do it with a much less bleeding, with less cost, essentially. And it makes me to explore more for the future. So, and the other categories we have is actually processes and tooling, enforced processes and tooling, and we're going to spend some time on the processing and tooling today. And then exploration, what can we do beyond culture, architecture, processes, and tooling to mitigate safety and security vulnerability from a language like C++. So architecture, I think we can talk about it probably for years, but I have only 2 slides on architecture. In safety medical devices, we care about risk-driven architecture. So as I mentioned, IEC 62304, they classify product from Class A, Class B, and Class C. And if your product, the holistic view of the product, if it's a Class C product, that doesn't mean every single software component within your product is a Class C. You could have multiple classes. Maybe you have a logging system. So if logging fails, am I going to hurt a patient? I don't think so, right? So logging could actually be a Class A software component, and then we have multiple other classes within the whole product, but the entire product is considered Class C. That's how IEC, the functional safety, is actually considering different classes. So based on this, I'd like to control and reduce risk. So I have a software item which, let's say, controls the robotic arms or the instruments. So those items, they are Class C, but let's say, and you have vision, which is also Class C, let's say, but you have logging, you have a bunch of different components that they actually may not be Class C or even Class B. So based on this, I'd like to control and reduce the risk. In the presence of adverse conditions such as fault or limited resources or limited performance, controlling and reducing the risk requires guaranteed resources and requires guaranteed performance. And these feeds into how am I going to logically or physically segregate software components. So as I mentioned, you have a Class A. Does a Class A software item should be in a real-time operating system or maybe even no operating system due to maybe time criticality, right? So in this case, I have to physically segregate the system, the software item based on their classes into, let's say, real-time operating system, maybe embedded system, into pure FPGA or bare metal, or even non-real-time operating system. And logical segregation as well. Even you can go further than that. Maybe in a real-time operating system, you can actually have different software components. You don't want them to interfere with each other, so you specify even more segregation, like putting on different cores, putting on different threads without them having to interfere with each other. So, and then at the end of the day, we want to extend the software, we want to maintain the software, so we need to reduce coupling and enhance cohesion here. Another way to see this is classifying it based on time response or time guarantees. So for many of them, let's say the logging, as I mentioned, it doesn't have to, if I miss messages on the logging site, I don't really care that much. It's not gonna cause severe, injury to the patient. It's a Class A software product. So I'm gonna classify that as non-real time. And all the way you can classify different components to, soft real time, firm real time, and hard real time. You can find different definitions for these kind of real time. So for instance, vision, let's make an example of vision. So vision, you have a, camera inside the patient body. It's not an open surgery, it's small incisions. So the surgeon has a viewer to see the camera, see the vision. So the vision, because we need guaranteed time response for vision, that shouldn't even go through an operating system to slow it down. So it goes through bare metal, essentially, maybe FPGA or any other devices that you can use to have guaranteed timing on them. We're gonna get back to this slide later when we talk about safety critical path and what coding practices we can use to ensure like hard real time or soft real time or non-real time components. So now let's talk about process and tooling. We have heard a lot about how can we do software hardening. This is just our perspective. There are many, many, many different ways that you can do software hardening. This is based on our experiences. So IEC 62304, as I mentioned, they talk about coding guidelines. They do not require it. They say if you use it, perfect, fine, but they do not require it. So in medical devices, unlike avionic or automotive, there is no safety critical coding guideline. So we have to pretty much stick with what automotive or avionic have. So for example, we use, let's say, MISRA 2023, the older one, not that great, but the new one, which is 2023, that targets CPP 17, a great safety critical coding guideline, AUTOSAR, again, for automotive, and then JSF++, which basically is for avionic. So we can adapt different techniques from those guidelines to enforce them, on the code base that uses C++. And then we have generic coding guidelines like, let's say, Google Style Guide or C++ Core Guideline. Some of these guidelines, they might have conflict with each other. So for that, you probably need some sort of internal coding guideline to ensure you address those conflicts within different coding guidelines. So compiler hardening, I think today in the keynote speaking, I wish my talk was before that, then they say she copied me, not I copied her. So the compiler hardening is very important. Specifically, you have to do it way earlier in the project. You can actually use OpenSSF. This is open source security foundation. They have a compiler option hardening for C and C++, specifically C++, and they prioritize memory safety. So this is not all the options that they tell you to use it in product. They have a giant page on what compiler option should be used in product or in development, specifically to target memory safety, and some of them for type safety and thread safety. So I have a bunch of examples here. Some of them are basically just compile time, so it won't let you to compile your code. Some of them are runtime flags. For instance, we have some of them are static, and the FDA actually recommends you should not have any warning or any error when you release software. So if you have, the idea is to slowly turn on the warning from the compiler perspective, and at the end of the day, use -w error as I have it here, -w error, -w all, and -w extra. This ensure all the warning you have turned on, they turn into errors, then you can compile your code, and then the software will release, it does not have any error. So a lot of example here, more example. And one thing that I think probably you guys have heard the word sanitizer more than the word CppCon throughout the conference. I'm gonna just allude to it here. So we have a lot of different sanitizers, address sanitizer, thread sanitizer, leak sanitizer, memory sanitizer, undefined behavior sanitizer. And recently, I think it was a talk on Monday by David and Chris on real-time sanitizer. Actually, before I attended their talk, and I didn't know they talk about it, just through the Clang documentation, I found it. It's very good. We haven't still used it. Looking forward to use this real-time sanitizer, perfect for safety critical system. And this sanitizers, they have a lot of performance hit, right? If you basically, it's a cybersecurity vulnerability for some of them if you use them in production. They have a lot of performance hit and they have vulnerabilities. But you can start from probably the unit test. So you can add the sanitizer perhaps from a unit test perspective. And then once you have a lot of testing sessions, you can add you can combine non-conflicting sanitizers. Let's say if address sanitizer does not conflict with leak sanitizer or the memory sanitizer, you can combine those and run them in some test session on the production code to ensure you catch bugs earlier, such as race condition, which is actually extremely hard to catch. So we talked about all this, sanitizers, the compiler hardening, and all this work. You require some sort of, extreme CI/CD, CT pipeline, right? So starting from the developer local environment. So having a rich IDE, having maybe the use of AI tools such as Copilot, being able to integrate static analysis tool and quality gates into the local development, and also being able to use the sanitizers locally, and all the way before even you make the commit to the code, before you make the commit, you have tons of guardrails to not make mistakes. And then you have the pre-commit hook. On the CI side, you have multi-platform build, you have multi-compiler build, and then you have the test build all the way to the sanitizer, all the way it gets to the CI static analysis tool, the quality gate, then code review at the end. Then the reviewers will be like, yeah, this code could have had a lot of errors that could have been cut through this process. So they think about design part of things, not necessarily the bugs that they may not have been able to catch. And then merging the code. This prevents to address a lot of hotspot in the code, security hotspots specifically, bugs and vulnerabilities. I talked about testing a little bit, like I mentioned. Testing, documenting testing, compiling tons of report on testing is extremely important. So for example, on a cybersecurity perspective, you have to have fuzzing. You have to have penetration testing, which is extremely important on the cybersecurity side, both from a hardware and software perspective. So penetration testing, a lot of time people only do it in-house using their own development or their own cybersecurity team, but that's not actually enough. You have to have unbiased penetration testing from third-party vendors to come in without any bias, check your code from 0 to 100, both hardware side and the software side, to ensure most of the vulnerabilities are actually addressed. We have, actually FDA requires you, by require I mean they tell you to do it, which is fault injection testing. So your system could have fault, a lot of faults. Some of these faults could be recoverable, some could be critical, and many different type of fault. You have to have a report that actually you tell them, for all these faults that I have, I inject them, this is what I see, from the system side, this is how I'm gonna recover, and all the report has to be submitted to FDA. So we have reliability testing, stress testing, simulation testing, SQA testing, performance testing, which is extremely important. So I think this is one of the last slides that I have for this piece, which is frequent upgrades. So medical device, when you start development, it takes probably, maybe 7 to 10 years for a very complex system, right? So you start from 7 years ago, you use, maybe Boost 1.53 or something like that, right? Being enabled to migrate away from older version and updating the software, in my opinion, is a superpower. The reason is your developers get access to new features. You address a lot of bugs within those older software, and most importantly, the vulnerability. You address a lot of vulnerabilities. So just being able to reduce that tech debt and being able to migrate away from older version to new version is extremely important. So getting back to this slide on the non-real-time, soft real-time, firm and hard real-time. So what I would like to avoid, once the system startups on the robotically assisted surgical platform, you have tons of checks. Once those checks pass, the instruments are within the surgeon, within the patient's body, and the surgeon is ready to do teleoperation or do surgery on the patient body, I have to avoid a bunch of different unsafe operations. So from a CPP perspective, we would like to identify the UBs and avoid them possibly, uninitialized variable. And all those, bugs or unsafe operations, undefined behavior, the static analysis tools or dynamic analysis tools, code reviews, they can catch it for you. We have to avoid every single one of them. And then we want to avoid non-deterministic behavior in the critical path, going from, the surgeon console controlling the instruments essentially. So we want to avoid dynamic memory allocation. You've heard this probably a lot in these conferences and in the past conferences. Exceptions, we want to avoid exceptions. And then from an OS level we want to avoid blocking calls, unnecessary locking, IO operation. We want to stick to async programming and primitives within STL. All right, I think Alex.
All right, thanks, Milad. Yes, thank you. All right, so this is CppCon, so I think we made an effort to at least show some CPP code in the next segment here. So I want to talk about how the safety critical path, how C++ code we write there might look different than C++ code written for other applications. One of the things Milad mentioned was we don't want to use dynamic memory allocation, at least after initialization. So first question is why? Why don't we want to use it? Well, one, it's non-deterministic in time. If we have to hit a deadline, we want to be sure we're going to hit it. We don't want to make a system call for memory that might take longer than we expect. We can have fragmentation in the memory heap and, absolutely just run out. This happens and, it's kind of like non-determinism in behavior in a way. We might not get what we ask for and we can't really do that, or maybe we can, but we better check it and handle it appropriately. So before we have tools like real-time sanitizer and performance constraints, how do we identify this when we're just looking through code review or writing our own code for the first time? It's not always obvious in C++ when dynamic memory allocation occurs. Often things are done by default. It looks nice for the programmer, but dynamic memory allocation is happening behind the scenes. So what can you look for? Look at STL. Is there an option to provide an allocator? That should raise some red flags that maybe allocation is going to happen. Do operations, methods of that class throw a bad alloc exception that's coming from the allocator? It's trying to get memory and failing to do so. It's probably using dynamic memory allocation. But you can kind of just think conceptually, what kind of things are going to need dynamic memory allocation? Things that we don't know the max size at compile time, things that might grow indefinitely in an unbounded way, standard vector, map, set, string. Things that actually hold something of a type that isn't known at compile time, a unique pointer to a parent class that might hold a derived class. We put that on the heap because we don't necessarily know how big that is when we're compiling. And things that use type erasure, again, we're putting some unknown type of unknown size at compile time somewhere. We can't really effectively put that on the stack, so we ask for dynamic memory. Now, sometimes dynamic memory allocation can be sneaky. For example, this line in main, we're logging a static string. I don't think that should allocate anything. It's a static string. Should be in my text section. But look at the signature on this log function. Takes a const reference to a std string. If this static string's long enough, we're going to construct a temporary std string, pass it to the log function, and go from there. So without even seeing it, I might be allocating memory. You got to watch out for these things. You could provide an overload that takes a simple C-style string. Better yet, you could take a standard string view, which this is a great use case for. Then you avoid that temporary and kind of unused standard string. So, looking at the documentation, looking at the code and thinking about it is great. We can catch this in code review, but still there's human error. We'd like to use things like static assertions, static analysis, dynamic analysis tools, unit tests. One approach that you can do is overload new in a unit test and kind of monitor the usage of that and fail the test if new is called. This can be pretty effective to prevent regressions. If you wrote this to not use new, you want to make sure no one else comes in and uses it. So this is a good technique, but it misses some things. It misses calls to malloc that don't use new. If your test framework needs to use new for mocks or something like that, this can be difficult. So I think if you saw the LLVM real-time sanitizer talk, the performance constraints attribute, those are even better tools. If you have those, I would do that instead. Those look like great tools. I'm excited to see them. So how do we write our code when we don't want to use dynamic memory allocation? Well, one approach, like we mentioned, well, we can do this in the initialization. We might fail initialization and stop, but that's pretty safe. We never even got started doing the safety critical thing. Once we get into our safety critical loop, I'm kind of modeling it here with this while loop. Presumably we're doing something else. We have to hit a deadline. Once we get there, we can avoid any kind of pushes to this vector, for example. But the reason I don't like this approach is because, well, now vector's there in our code base, right next to all our safety critical stuff. It would be very easy for someone to come in and think, great, I can use vector here. I can use make unique. I can use these things, they're used over there, why not here? If I'm looking at a code without looking at the whole picture, I might think this stuff's okay. It's easy to get regressions. Another approach would be to use the allocator, provide the allocator parameters to your STL types, use those instead, maybe use an arena allocator all at the beginning, and then just go from there. Also in practice, I don't like this one too much. Those APIs are designed to kind of use the dynamic memory allocation and throw exceptions on failure. We mentioned exceptions aren't really good in the safety critical path either. So in practice, this technique, I don't see it too much. But there are some good containers out there kind of designed to live on the stack. Things like from Boost, static vector, which will have a max size. You can't go beyond, but you can grow from 0 to that max size as if it was a vector. Small vector does the same thing, though once you go past that max size, you'll start asking for memory from an allocator. You can use kind of wrappers on top of these, flat set, flat map to get your associative container behavior on those using the stack. We also have, of course, good old standard array. If you know the size at compile time and just need to have a fixed size collection, that's great. Chromium provides a few other similar containers you can put on the stack. These are all good tools. So, kind of outside of the critical path, you might see code like this. We're creating some derived types, pushing them into a collection, pointing to the interface type, using standard unique pointer, creating a vector of unfixed size. So we're asking for dynamic memory here. Here I'm kind of halfway doing the right thing. I'm saying no throw for my call to new, so I can check the result. But then, of course, vector might still throw exceptions, so I'm not free of that exception world. But then once I get done with that, I have my nice generic loop. I loop through my workers, ask them to do work. How would I rewrite this in a safety critical area? Well, we have these static containers array. There was only 2 things there. I can use that. We know we can use things like std variant and not need to put these things on the heap. So that works pretty well. I change my call to use visit, and I can have pretty much the similar behavior. Call these as if they're 2 generic objects that do some generic thing. But really, I want to step back and rethink this. Like, why do I need to be so generic? Maybe I don't. Often I see kind of generic by default. Maybe that's not the right thing for me here. Maybe I'd rather just have simple stack variables. I have 2 of them. I put them on the stack. They're concrete types. I know exactly what they are. I can give them better names because I'm not trying to fit them into some generic paradigm. And the code's very nice and simple, and I'm avoiding the heap. So exceptions, I won't get into too much detail because they might use the heap, because they might be non-deterministic in time. We want to avoid those for the reasons we've discussed. There's a lot of other tools we can use to communicate some kind of alternative return or some kind of failure. Optional types like std optional, result types like std expected. Boost provides some versions of these. Other third-party libraries provide versions of these. You can use error code, system error. I don't really want to go into the details here for time, but these are all, depending on your use case, these could all fit your need. So we talked about non-determinism in time, and this isn't just about language features, but actually what you're doing. We want to avoid things like file I/O when we're asking, the file system for something. We're not guaranteed to get it back in some bounded time. Network I/O, acquiring a lock on a mutex, for example, the other holder of that lock, who knows when they're going to give it up, or when the OS is going to give us that. So you might see code like this outside of the safety critical context. Here again, I'm kind of modeling my safety critical step in this while loop. At the top, I get some lock on a mutex. Then I start processing items from this queue. Queue front, get the item, process it. Below that, assume there's some safety critical thing that has to happen by a deadline. Well, this is not good for two reasons. The lock guard is a non-deterministic lock. And then here, the amount of processing we do, since we're draining that queue, we actually may not have control over that. It depends. Maybe we control how that queue gets filled. But if we don't, we could have some foreign process making us stay in our iteration too long, missing our critical deadline. This is also a problem if that's a safety class, a low risk class process. It might become a high risk class process if it can cause us to overflow our step there by filling our queue too much. So we have to be careful about things like this. So we're going to avoid blocking calls. We're going to change mutex use. We're going to try to find some good weight-free data structures or containers we can use to communicate information. One good example is Boost's lock-free single producer, single consumer queue. Unfortunately, we do have to think about this a little bit more now because we have to give that a max size at construction. We better analyze our system, make sure we know what that max size should be, and make sure we know what to do when that max size is exceeded. The other problem is we don't want to consume everything in there necessarily. We want to make sure we're safe. If someone does the wrong thing by accident or on purpose and pushes a ton of data into that queue. So we want to bound that. Maybe we consume just one item per step and then do our safety critical stuff, make sure we hit that deadline. Maybe we do 10 items per step, but as long as there's some reasonable limit. And I do want to get back to why C++. Another great weapon we have in C++ is the zero overhead principle. That means I can effectively, in code review, kind of just throw away the arguments of like, I did it this way because of performance. I can say, do it the less error-prone way, do it the safer way. You're going to get performance, trust me. Just a simple example, not meant to be statistically meaningful, but a raw for loop written on the left, basically re-implementing findIf and using STL findIf on the right. We can benchmark that. With optimizations, we can see the optimizer does a great job and the right performs better, the yellow line. We can still mess that up. We can swap begin and end or something, do something like that, but there's less places we can mess that up here. So I prefer that approach. The code is more expressive. The name of the function says what you're trying to do. So I love being able to advocate for these type of uses in code review and kind of dismiss performance-based objections. And I'll hand it back to my colleague Milad to finish it off.
All right, I added these slides, so I'm going to speak to it. So basically, we want to talk about near zero overhead abstraction to fight for safety. So we have a lot of abstractions in CPP that could be used for safety. I mean, one of them we are familiar with, unique pointer, almost always has to be the default, but it's not a silver bullet. So it comes with some unsafety or unsafe behavior or API as well. So in unique pointers, we have APIs like get and release. So get gives you the raw pointer from the unique pointers, and release actually releases the ownership from the unique pointer and gives it to the caller. We have to avoid all these type of, even though unique pointer is a very safe feature, but it comes with this API. So we have to only use it in cases where we deal with like legacy code or third-party libraries that they use some function that uses only raw pointers, either a legacy CPP or a maybe legacy or third-party library on the C side. So if the documentation says I'm going to take care of the ownership, we use release. If the documentation says I just manipulate the pointer without any ownership manipulation, I'm going to just use the get one. This is the only situation we have to use this type of unsafe API from one of the safest features within C++, which is a unique pointer. So final words. So we do a lot of things to make C++, the usage of C++ safer, right? But that comes with a lot of trade-off, right? So one of the main trade-off that we possibly is making is actually performance, right? But that's not always the case. Sometimes it is. Let's say if you want to check for a pointer not being null at every single tick from a high frequency control loop, sure, that could be expensive, right? You are trading off some performance for safety for performance. But in most of the cases on the safety critical path, we are actually making the system to be a lot faster, like removing dynamic memory allocation, for example. Dynamic memory allocation essentially is a lot slower than having things on stack or having it to be pre-allocated, or removing exception essentially. So that makes your code a lot faster. So we actually gain performance by making the code safer. And then trading correctness for safety. Almost always safer code is more correct, but sometimes implicitly the code could be a little bit incorrect. So 2 examples I have here is static analysis tool. So you write some code, static analysis tools tells you, hey, there might be some mistakes here. So you write more code. The fact that you write more code, that could contribute some bug to the code base, right? So that's some sort of incorrectness you could get from enforcing like safety on the CPP side of things. And also degraded performance. In some cases, your client, your customer actually depends on the performance you give them. So if your performance goes down, that's a less correct system for that client essentially. So flexibility, of course. If you have a lot of CPP, as Herb Sauter mentions, it gives you a lot of knives to play with. You are absolutely free to use a lot of raw pointers, very low level concepts, right? That's much more flexible. But if you use near zero overhead abstractions construct in C++, that's way less flexible. But I'd like to make that trade-off essentially to gain safety for the system. And then the last one is trading cost for safety. Of course, doing all these CI/CD pipelines, all these safe constructs that we have, they require a lot of engineering hours. They require a lot of resources and essentially a lot of infrastructure. So you have to pay a lot of money for these kind of things. So safer usage of C++ is a lot more expensive. So takeaways, as I mentioned, building safe and complex medical devices are actually extremely hard. Standards, absolutely necessary. Regulatory documents and reports are absolutely required, but they are not sufficient. So software is a key part of the problem within the medical devices, and given the cybersecurity threat, and it will be for the foreseeable future as well. Testing alone, as I mentioned, is not sufficient. We have to have a fail-safe design mechanism in place. And then safety in CPP can be achieved through strong culture, robust architecture, effective tooling, and rigorous processes. And then at the end of the day, everything is a trade-off. There is no simple solution. One last thing, so we have a lot of opportunities within J&J, especially in our Bay Area offices for robotically assisted surgical platform development. We heavily use C++, and if you know anyone or yourself want to apply for these jobs, please go to our career or reach out to us after the presentation. We have a bunch of people here from J&J and talk to us. And then last but not the least, my friend and our colleague, Samuel Previtt, tomorrow he's in the talk right here. He's going to talk about why is my build so slow on the Adams Ballroom, the largest room, at 2 p.m. tomorrow. Probably for the past 3 years, I have heard this talk for 3 complete years from Sam, but I'm willing to again sit in the talk tomorrow to listen to it, so please attend. Thank you so much, and if you have any questions. Thank you.
Hey, thank you for the talk.
Sure.
So you were talking about different ways to mitigate some pain points and to avoid certain things in the safety critical path. My understanding is that the surgeon is not in the robot, and there has to be communication from one place to another place. Mm-hmm. And I believe that you said something about avoiding the network or avoiding communication in the safety critical path. So how do you mitigate something like that?
So. Yeah, if you have, let's say, a multiple platform within your system, right? So you have to have some sort of communication. I think the network, do you mean the network I/O?
I can.
You can take it? Okay.
Yeah. So one thing you can do is handle that I/O outside of your safety critical path and communicate from that outside handling to your safety critical path in a safe way. For example, we saw the single producer, single consumer queue, weight-free, limited number of messages or whatever we want to call it, put there for your safety critical thread to pick up and process. And that way you can get that kind of separation. It's a lot of work, but sometimes you have to do it, right?
Thank you.
I can add one more thing here. So you do have communication. So based on the classes we have, right? So like, for example, UDP communication, that's some sort of real-time communication, but it's not a hard real-time communication. So in those cases, yeah, we have communication between, multiple platforms from surgeon all the way to the patient side. But in those cases, because the time guarantee is a little bit lower, the practices could be just a bit different as well. Yeah,
Thanks, Skip.
no problem.
So you talked about disallowing dynamic memory allocation once you've entered your safety critical portion of the code. What about stack utilization? Do you have rules like disallowing recursive calls or tools that you use to track stack usage? How do you ensure that you don't run out of stack?
Yeah, it's a good point. We cheat a little bit because we also can't act like the stack can't fail, right? We could overflow the stack. Mostly it's done empirically from what I see.
Mm-hmm.
So we've seen it, not overflow. We're not putting image data, things like that on the stack. There's large things we just can't do.
Yeah. So we do a lot of like pre-allocation, and also we do like things like memory locking from the OS calls, right? So for example, if you have a process, you pre-allocate, let's say, 100 megabyte from the heap. You memory lock it, and then other processes within the system, none of them can actually access these piece of memory that is pre-allocated to reduce the latency for the critical path. So it's not necessarily, everything is not necessarily on stack, because for example, the default size for stack on a Linux machine could be, 8 megabyte or something, right? But we might have way more than that. So memory locking is another mechanism for processes to pre-allocate to reduce the latency. And empirically, that has actually reduced latency drastically for the heap allocation, for the pre-allocating the heap and doing like basically pushing back to stack to vectors and things like that.
Great talk. I was curious, what does the process of bringing new dependencies or upgrading third-party stuff that you guys are using look like, and how does that affect, the overall timeline of the product or some feature that you're pushing? Because I imagine there could be like a trade-off of like using like the old Boost version because that's been vetted, but new one has features that could have performance improvements, but you need to like redo that vetting process. Like I was curious, how does that look like?
Yeah, these two are our experts in build system.
Yeah. I mean, I can't talk about our timeline for other reasons, but I mean, if you've been to the other talks here on dependency management, I think we have the same problems. It all looks familiar in the C++ world. Managing dependencies still feels like it's not solved to me. But like Milad mentioned, upgrading is valuable. It's also motivated by safety. We need to, if a security flaw was fixed, we need that version. So I think
a lot of it is like extensive testing too, right? So a lot of time we need, let's say, a new version of some libraries, but it's not easy because some of them could be a pretty high jump. Let's say if you want to get access to some LTS, for some vendors, you go from, let's say, version 6 to version 8 or 7, which is the LTS one, because you could get some API changes or drastic change within the code base. You require a lot of effort. So you do incremental changes on the software updates.
The advantage we do have in our space is our system's pretty well controlled by us. So if we want to put everything to one version, it's pretty much our decision. We don't have clients depending on us using, an older version. We have pretty good control. We need to have control. So,
Yeah, makes sense. Thank you.
I just jumped the line.
Same question. We already asked.
No worries.
Yeah, and this is on the same topic as well. And thanks for the talk. You guys had talked about verifying all of your soup, and in an earlier slide you showed C++ connecting with a bunch of dependencies. Are you implying that you're doing validation on all of the dependencies that you listed, like for instance ROS and TensorFlow? And if so, are you digging into recursively into all of those packages dependencies?
So I can't speak to the exact process we do. I think mainly is on validating the output of, basically imagine you have a process or a software component that depends on, TensorFlow, OpenCV or whatever, right? So given the output of your, like the binary you have, where you deploy this and then you have some, let's say, input to that and some output to this, based on the expected output, that's how we validate. It's not like we go to the entire of those components and then validate TensorFlow or the compilers. We validate the output of those components as a soup, basically. So it's not the exact software item, it's exact dependency, it's the output of the binaries that we have that created from those, that depend on those software
Got it.
items.
Thank you.
Yeah, no problem. Thank you, guys.
All right, thank you.